intelligence at all, or some sort of organization, order, I mean, that usually means that there's a pattern there. No matter what you're looking at, from the very small, like crystals and microorganisms, all the way up to galaxies and super galaxies. I mean, there's patterns everywhere, and that's mostly what you're trying to deal with as a human, is recognizing and dealing with patterns. And patterns have pattern spaces. In other words, all the different patterns that are linked to each other in a certain space. All right, so all plants and animals are made up of patterns of cells, and cells and minerals are built with patterns of molecules and atoms are patterns of protons, neutrons, and electrons. And music consists of sound patterns, weather moves and weather patterns, and so on. It's just patterns all over the place. So in a system like MathPiper, which again, it's a programming language, but its focus is more mathematical things. There's a bunch of tools in there that play with patterns. So one of them is permutations list. Now these little underscores in front of the names are just, they turn these into constants. I could have used strings with the double quotes, but sometimes it's easier just to use a constant. So I put Bill, Mary, and Tom just in a list. And I ran that, or sent that list to permutations list, and what did it do? Like it returned a list of lists, but what did it do just in English? Like, what does it look like a permutation is?
Every possible outcome.
Yeah, every way that you can arrange those, now that's a permutation. So, MathPiper has a tool that'll just do that for you. So these are permutation patterns of just the three things that I put in. All right, so what are all the different ways we can arrange A and B? Well, you can arrange it A, B, or B, A. There's not a lot of variation there. What happens if we had three letters, A, B, C? Well, A, B, C, A, C, B, C, A, B, and so on. Well, what about four patterns? You can see that every time you add one more pattern, or one more letter, the number of patterns is going up in a nonlinear way. You're getting more and more. Just with a little bit of input, you can get a lot of output. And like I said, 1, 2, 3, 4, 5. So you put in 5 letters and just look at all the patterns you can get out of that. All right, another little tool here is called table form, that if you don't want to see a list, its elements just go left to right, left to right, left to right, you can put them all top to bottom by just running a list through table form, and it'll just put them one after the other, one on a line, just to make them easier to read. All right, here's a little program. I take A through H, run that through permutations list, and what we're going to do is count how many patterns there are. So like how many sublists come out of that. So here I have a counter, number of patterns assigned at the 0, and for each, now this is a procedure you haven't seen yet. But most programming languages have something similar to this. If you pass in a list here, and you run it through for each, what it'll do is, instead of you having to use an index to reach into the list to copy elements out, it'll pull them out for you. So the first element in the list, it'll assign to this variable, and then you can do something with it. And then the next element in the list, it'll pull it out. And so it's less typing, just a for each. It's used a lot, but the problem is you don't get an index to know where it came from in the list. You just know it's one of them in the list. But we just keep pulling the patterns out like this. Pull this one out, and then pull this one out, and just a copy of it, not the original. But what are we doing inside the body of the for each once we have one of those patterns assigned to this variable? Then we're just counting it. We're not putting it in another list. We don't really care what it is. We just want to know how many there are. And then give us 2 new lines, and then echo, the number of patterns is number of patterns. All right, so this is a little procedure, or a little piece of code here. And it says, all right, these letters, A through H, if you ask for their permutation, you get 40,320 different ways you can arrange those letters, which is, amazing for just that many letters. Well, this is another way you could do it. You can just say, hey, permutations list returns a list. What's the length of the list? And you get the same. In programming, there's usually multiple ways to accomplish the same goal. Some of them require less typing by the user. Some of them run faster. It's a trade-off, just deciding which one you want to use in any given situation. All right, we can also time how long it takes to do this with this special time procedure, which you don't use, but I use it in some of my example code. So it's like, well, how long did it take to make all the permutations of A through H? All right, so in this case, there again is 40,320 patterns. It took a little over 2 seconds to put together, but there's a counting time and a total time. So what's the counting time? So here's how much time it took to actually generate the patterns, and then down here, this is how much time it took to count them. That's how long they took to generate. This is how long they took to count, and it took about 2.5 seconds when you add those together for the same thing. But if you increase the number of letters to 9 or higher, the pattern space that's generated becomes too large for the computer to handle. But what if we wanted to know how many patterns could be generated by 15, 20 or more letters? Is there a way to determine this? And the answer is yes, by using the permutations procedure. Now, with a computer, you don't really need the computer, but the computer makes it so much easier. There's 2 ways to figure things out in the world. One way is to just observe it, to actually make the things and look at them and count them. Another way is to calculate them. Well, there's 3 ways. You can make the physical things and count them, or step 2, in a computer, you could make simulated versions of those physical things and count the simulated things, which a computer's great at doing that. Or if it just becomes too hard for the computer to do it even that way, then you just resort to mathematics where you can calculate the answer. All right, so permutations is really interesting, this procedure. So how many different permutations can we get out of just one thing? And it says, well, just one. I mean, that's it. Well, how many different ways can you present 2 things? Well, 2 different ways. Well, what about 3 things? All right, well, there's 6 ways that you can arrange 3 things. What about 4 things? 24. But look at the time it's taken to calculate this. See here, it's 0.0007 seconds. And then when I double it, it's 0.0009 seconds, just a little bit more. And then I go one more than that. We're still like 0.0007 seconds, 0.008 seconds. So really, as we're adding the number of things to permute, it's not taking really that any longer to calculate. I mean, all the variation here is just kind of random. So 6 things, 7 things, 8 things, 9 things, and we're still. So this is the power of mathematics over even what a computer can do by making simulated things. Look at this, 20 things. So it's a little bit longer, but not much. 40 things, a little bit longer, but not much. Look how long 40. This is how, it's like if you had 40 things, this is how many ways that they can be arranged. There's not even the name maybe for that number, it's so big. Even 20 things, it's a really big number. All right. So what I'm showing here is something called tools for moving through a pattern space. And by tools, software is also a tool. So these are software tools for moving through a pattern space. One of the nice things about patterns, if you look at them abstractly, so what happens is that you don't make tools, we went over this before, but it's worth repeating. You don't make specific tools for specific jobs. Usually what you try to do is you make a tool that can be used across a number of different jobs, even if they're kind of similar, these jobs, but you don't just make one tool for this specific job. So if I had a nail that I was going to hammer into a wall, I don't have one nail that I make by hand and then make the hammer just for that nail, and that hammer can only nail in that nail. It's like, I mean, there are situations where that happens, where you have a one-off tool on something usually that's big, that just needs to be done once, or even sometimes something small. I mean, this happens all the time. I repair cars as a hobby, and sometimes, you know, I can't get my hand around this specific engine, around the back, around the side to get at this little nut here. And it wouldn't make sense for me to make a general purpose tool that can do a range of those things, because it's a very specific application. And so you'll spend time to make this one tool so that one time you can get your hand in there and undo the nut. It's a lot cheaper than like pulling the engine or taking it to somebody. But most of the time when you're making a tool, you're trying to make it general purpose to a certain extent so you can use it for a range of applications. Well, the same thing with these pattern tools, and especially you know, in software, that because the patterns are similar, no matter you're looking at the little patterns, the medium-sized ones, all the way up to the galaxy-sized ones, these patterns have a number of things in common that you can make tools that can deal with all of them, like the permutations. You know, it doesn't matter whether I'm taking cells in a petri dish and doing the permutation on that, or stars in a galaxy and permutating those. They're hugely different in size, but the same tool will be applied to it. All right, so a common thing that needs to be done with a pattern space is to move through it. For example, here's a familiar pattern space that consists of the numbers from 1 to 100. Here's a piece of notation, again, that you've not seen before. 1 space dot dot space 100. And what did it do? Yeah, internally it created a list of the integers from 1 to 100. Well, how come I haven't shown you this before? I mean, I could give you a layout that would say, hey, make the code that will generate a list that has the integers from 1 to 100 in it, and you would go through some sort of little while loop or a for loop, and you could do it. But somebody at some point in time said, hey, we do this so often, we create a list of integers so often. What's the easiest way I can think of, or at least an extremely very easy way, that we can do this with as little typing as possible? And they came up with this operator, the dot dot operator, and you have to have a space on either side of it, but 1 space dot dot space 100, it'll just generate them for you. Why don't I show you that? Well, because if I showed you that, you would learn that, but you wouldn't learn how to do it manually. You wouldn't learn that in any programming language where they don't have this operator, you know, you can just do it with a while loop or a for loop. It's warm in here, isn't it? You can take off your jacket.
I did.
Really?
This is my long sleeve
Oh.
shirt on.
Oh, no.
And, I forgot it being hot up here. Oh well, I'll be all right.
Yeah, I'll try to move through this quick.
Oh no, you're.
Yeah, that's
good,
what we
sir.
need is a tool that moves through the lecture quicker. All right, so walking through a pattern space with a pencil and paper, you could do this. If I was going to add up the numbers between 1 and 100, let's say that's my goal, and I could on a piece of paper, 1 plus 2 plus 3 plus 4, you could do it. It would be a long time, and they used to do it this way all the time, but very few people do it this way anymore, but you could do it. So would it be a little bit faster, like flying a spacecraft through it? This is what you've been doing. You've been flying spacecraft around with this code. Sum becomes 0, index becomes 1, and while index is less than or equal to 100, whatever the current sum is, add the current index to it, take that sum and assign it back over sum and just sum it up. Which is very, very powerful. And when we run it, it says, all right, if you take the first 100 integers and add them together, it comes out to 5,050. And it takes, you know, a relatively short amount of time to do that. Well, how fast could a human do it by hand? Well, let's calculate it. So let's say that it took a human, one that's pretty fast, doing this in 10 minutes, adding them up. What we're calculating here is that the computer can do it about 100,000 times faster. And MathPiper's not a very fast language. It's not designed to be. But it's still 100,000 times faster than a human doing it by hand if we assume that a human can take 10 minutes to do it. And so now it's saying, hey, even though you've got a computer, a pattern space can be so big that you can't deal with it. It like overruns the computer's memory. Even though you might have 4 billion memory locations in there, it's too big for it. So let's try this out. I'm going to make a procedure called sum of integers. And the highest integer that it's going to sum up to is passed in this variable here. Sum becomes 0, index becomes 1, and while index is less than or equal to the highest integer, just sum up to the highest one. So we have a procedure. And now what we're going to do is use for each to grab the number 100, 1,000, 10,000, 100,000, and 1,000,000, and run it through sum of integers and then collect the data. This is the type of stuff that a beginner class is designed to do, is that whatever, like if you're making your own company or you're helping somebody else with their company, you're an employee, whatever, there's just answers that need to be found for problems, all sorts of problems. And this, you might have some sort of a problem like this. You can just throw together some code and get an answer and make your boss happy. All right, so if the high number is 100, it still sums to 5,050, and it takes 0.007 seconds. If we sum to 1,000 this way, it's 50,500, takes longer. If we go to 10,000, that's the sum, a little bit longer. If we go to 100,000, that's the sum. Now we're getting in like 3.6 seconds. And then your million, that's the sum. And now we're at 35 seconds. And if you go higher, it's just, MathPiper will take a very, very long time to do it. Well, can we still solve the problem using more like math as the technique? And the answer is yes. All right, this is going back to, if you have a problem, solve a simpler problem that's like it first to get your mind around it, and then scale it up to the more difficult problem. All right, and this is one of there's a lot of interesting stories about people from the past that did things that were remarkable, and one of them is this story with Gauss. He was a mathematician, a genius mathematician. And what happened is that, this was a long time ago, 1700s or something like that, 1600s maybe. But what happened is that young Gauss was in class, math class, and his math teacher was lazy. And what the math teacher would do is the students would come in and he says, all right, on a piece of paper, add up the integers from 1 to 100. And while the students were doing that, what do you think the lazy math teacher was doing? What's your guess?
Huh?
What do you think the math teacher was doing? So it'd be like me saying,
You did the same thing I did at the exact same time. That's the reason I laughed.
Oh, really? Yeah. Well. So this is the thing, like if I did this, if I said, all right, take out a piece of paper, every one of you, and add up the numbers, integers from 1 to 100, it'd probably take you more than 10 minutes to do it. What would I do? Like if I wanted to surf the net, I would just do that. You guys would be doing that, I'd be surfing the net. Well, they didn't have the net back then, but they did have the newspaper, and Gauss's math teacher would just read the newspaper. But what happened is that, so what usually would have taken the students 40 minutes to do, so the math teacher could have gotten through quite a bit of the newspaper. In about 5 minutes, little Gauss came up and said, I'm done. And the math teacher's like, nah, you can't be done. And then he looked at it and it's like, he got the answer. It's like, how did you do this? Well, this is what little young Gauss did. Instead of just like kind of linearly and mindlessly just doing the problem, he just started looking at this. And again, he didn't do it with 100. He said, let me see if I could do with a smaller problem, which is 10. So what he did is he put the integers 1 through 10 in a row, and underneath it, he put the same integers in reverse order. Now, can you see any patterns that you could make with this configuration? There is a pattern here. What's remarkable about this?
You've got two of the same number?
Well, you do, but, I mean, like what operations can you do? What would pop out of this? Like, what can we do with 10 and 1?
Add
Add, like, what is 10 plus 1?
11.
11. What's 9 plus 2?
11.
11. What's 8 plus 3? Yeah, so there's a pattern here, like a pattern within a pattern. So you look at these numbers like this, and then you add them up, and it's like, oh wow, look at this. They all add up to 11. And then Gauss said, well, wait a minute. And so now I can, play with MathPiper a little bit more here. I can say, all right, well, generate a list from 1 to 10, and then generate the backwards list in reverse order 10 to 1. Now this is something I haven't shown you, but you could take two lists and add them together, and it'll take the first two, add them, and put them here, and the second, two, and add them here. So this actually works. 1, 2, 3 plus 1, 1, 1 gives me 2, 3, 4, with those adding 1 each time. So we can take 1 to 10 and add it to 10 to 1, and of course they all add up to 11. But is that true for all numbers? Well, we're not at the level of doing proofs, so this isn't a math class. We could do a proof on this. I mean, this is like one of the classic proofs when they teach you how to do proofs. Like mathematically, you can prove that for every set of numbers like this will always happen. But if you're not able or not wanting to do a proof, you could use the computer with your little bit of code knowledge and just poke around a little bit and see what happens. All right, so 1 to 2 and 2 to 1, they add up to 3. 1 to 3, 3 to 1 add up to 4. 1 to 4, 4 to 1 add up to 5. So what's the pattern here? Yeah, so however many elements in the list that you have, like there's 8, like 1 to 8, there's 8 elements. They're always going to add the one more than that. So if there's 8 elements, they'll add the 9. If there's 7 elements, they'll add the 8, and so on. If there's 15 elements, they'll add the 16. If there's 20 elements, they'll add the 21. So this seems to be a pretty solid pattern. All right, now we're going to go to mathematics notation, which is like a programming language. Mathematics, what's partially hard about it, so something like MathPiper, so like how long have you been being taught math? I mean, they probably started you off on some elementary math, like really simple stuff, maybe kindergarten, first grade, and then you've had 12 years of that, plus whatever you've had in college. You've had math for years and years and years, and it's still really tough. You've had MathPiper for, I don't know, a little over half a semester, and you've done quite a bit with it, just in a lot less time, even though it's not easy, but it's more verbose. It's like spread out a little bit more. You can actually see the pieces and get your mind around it. But mathematics is designed to take really complex stuff and crunch the notation down so you can think of and deal with really big ideas with just a little bit of writing. All right. So now we're going to turn this into a kind of a formula. So n columns. If I have n columns, like 10 columns, what does it sum to? So if I have n columns, which makes this an abstract problem, it's like I don't care how many columns, just however many columns I have, I'm going to call that n. Well, what will n columns sum to? Help me out here. We're going to cook. Just read it. You don't even have to understand it. It's n plus 1. Give me like the illusion that you're getting this. So no matter how many columns of numbers you have, like in this case n is 10, 10 plus 1 is 11. If you had 5 columns, 5 plus 1 is 6, and so on. So he did this. He was just like, in his 5 or 10 minutes, he was scratching this out. So however many columns I have, they're always going to add to one higher than that number of columns. So now what value would we get if we multiplied n and n plus 1 together like this? So if I did n times n plus 1, or times the quantity n plus 1, Yeah, so 10 times 10 plus 1 is 110. Now, what did it actually add up to? The very first one. I have to go backwards a ways. Oh, I didn't go down to 10. What does 10 add to? I tell you what, I'm going to show you here in a moment, so. Oh, man, I lost it. All right, just don't look up here, it'll make you sick. Let me just go down to where I was.
Like on a sailboat.
What did you say?
I said like a sailboat.
Right, yeah, you're on a sailboat, you're gonna, All right,
There we go.
here we are. So 10 times 10 plus 1 is a 110, but the numbers from 1 to 10 actually add up to 55. So sum of integers, like, here we still have our sum of integers procedure in memory here. What's the sum of the integers from 1 to 10? Well, it's 55. Well, this calculation gave us 110, but when I did it for real, it's 55. What's the relationship between the 110 and the 55?
Half.
It's half. So Gauss said, all right, what would happen if I did this? Number of columns times the number of columns plus 1 all over 2. And it turns out that that's the trick. So 10 times 10 plus 1 all over 2 is 55. Sum of integers is 55. Well, what about 100 times 100 plus 1 divided by 2 is 50/50, and sum of integers is 50/50. And it turns out it works for every one of them. We get the exact same numbers as if we just counted them in the simulation. So then what I can do is that instead of having just sum of integers, I can make a procedure called fast sum of integers that doesn't use any loops. It just uses this calculation. And this is really, really fast, and really almost as like you could have these whopping huge numbers and it'll just calculate it really quick. And this is why mathematics, well, at least one of the reasons it's so powerful, is it can just deal with almost unlimited amounts of complexity and still give you your answers really fast. All right, so we're going to go through the same for each type of a thing again with the same 100, 1,000, 10,000, whatever, but we're going to run it through fast sum of integers instead of sum of integers. And this is what we get. We're still getting the same sums, but here's the calculation times. Notice that they're not changing very much. It's just, even with the very biggest one, it can just do that calculation really quick. So that's just one point I wanted to show you, is that one step beyond what you're being taught in this class, which is to kind of use the computer as a simulator. If you run out of steam even that way, what's beyond there is just math, and you can put the math right into the code. So this is where I say that, having one step above a spacecraft is like having the ability to jump through hyperspace from one point of your pattern space to another really quick. All right. All right, so summing without applying an operation. This is the mathematics notation for sum. Just what we did with that, like 1 plus 2 plus 3 plus 4, the little loop that does a summer. Well, this is that same idea in math, where x becomes 1, x is a variable, x becomes 1, and it's going to go all the way to 3, one integer at a time. And while it's going from 1 to 3, just sum it up. So that's how you do that same idea in math. So the sum of the numbers from 1 to 3 would be equal to 1 plus 2 plus 3, which equals 6. And this is what it looks like in code. If I'm going to sum from 1 to 3, x becomes 1, and while x is less than or equal to 3, just sum it up, and there you go. So what was that little bit of code in math, we've expanded to a few lines in computer code. And so now, we can sum 2 times x from 1 to 3. Each time through the little mental loop here, we multiply it by 2, so then we end up with 12. And all we did was, instead of sum equals sum plus x equals sum equals sum, or sum becomes sum plus 2 times x. Yeah, okay, mathematical notation was designed to relay complex ideas with a minimal amount of typing or writing. Knowing how to program makes learning math easier. I think a large part of the problem with mathematics education is that the mathematicians have been doing the shorthand notation for so long, they don't even know how to unpack it, so you can actually grasp the concepts. I find that if you're learning a piece of mathematics and then you're also learning the same techniques in computer programming, you can use the computer program to kind of help explain what's happening in the condensed math notation. Like, one of the things they do is the mathematicians don't actually use the multiplication operator. What do they do for multiplication?
Nothing.
Right, it's called juxtaposition. It saves them when having to do, a multiplication symbol, which is great if you know what you're doing, but how many young people don't understand, that there's like nothing there, so that means multiplication, but there's nothing there. You just have to kind of know it and remember it. And all right. Go ahead and take a 10-minute break, just because it's so freaking hot.